So let's pick up with number 31. We have 4 different compounds and we want to identify the substrate that will be most reactive under SN1 conditions. So in each of these cases, the bromine is going to leave. So I'm going to go ahead and facilitate that process, and we'll look at the intermediates. So the defining characteristic of an SN1 reaction is that it leaves a carbocation intermediate. And we know that carbocation intermediates can be stabilized either by resonance or by induction. And so our carbocations are as follows. And we can characterize all of these. The one to the far left, answer choice A, is best characterized as benzylic. Choice B would be best characterized as secondary. Choice C, tertiary. And choice D, allylic. Remember, resonance effect trumps inductive effect, and benzylic is better because you can make more resonant structures. So the credited response to number 31 is A. Let's move on to number 32. So 32 is similar, but now we're looking at the rate limiting step in an SN1 reaction. And so choice A is the nucleophilic attack, which we know is a legitimate mechanistic step in an SN1 reaction. Choice B shows homolytic bond dissociation. This is not a characteristic of an SN1 reaction. I think this should be very quickly discarded. So we're going to discard B. C shows heterolytic bond dissociation, which does occur. The problem is it shows the electrons going to the less electronegative element. That, of course, violates the principle of arrow pushing in terms of the electron pair should always go to the more electronegative atom. And finally, D shows the same process, only this time it shows it with proper arrow pushing. And so you're generating the carbocation in D, you're alleviating the carbocation in A. The carbocation is going to be the least stable intermediate. That will be our rate limiting step. And as such, D is the credited response for number 32. Moving on, let's go to number 33. You want the most reactive substrate under SN2 conditions. So you're looking for primary substrates, methyl substrates with really good leaving groups. All of these substrates are primary, so the difference is going to be in the nature of the leaving group. And I think a lot of you may have been tempted to pick the tosylate. But in fact, we see that alkyl halides are by far and away the most common substrate used in substitution reactions. And so answer choice A is going to be the credited response in number 33. Moving on to number 34. Which of the following species cannot serve as a Lewis base? Let's just cut to the chase on this one. You have an aluminum atom, which makes 3 bonds, all in the same plane, by the way, to 3 chlorine atoms. You have a p orbital lobe that comes directly towards you, the viewer, right out of the screen. I'm going to attempt to render that in 3 dimensions. There's also a p orbital lobe that goes away from you, the viewer, into the plane of the screen. And I'm going to attempt to render that in 3 dimensions. That means we can accept electron density into the top p orbital lobe or the bottom p orbital lobe. This means that this is a great electrophile, so this is a strong Lewis acid. But because there's no electron density in these p orbitals, it cannot act as a Lewis base. Therefore, D is the credited response for number 34. Let's take a look at number 35. We want the relationship between the following pairs of structures. We've seen a problem like this already. So we can go ahead and apply our flipping 2 labels twice strategy. So we've got H and F. We have Cl and H. And then on the other compound, we have F and H. And we have Cl and H. What I want to do is I want to flip 2 labels twice. If I flip 2 labels twice and I end up with this structure, then they're the same. So if one is S, the other is S. If I only have to flip labels once to get this, then they are enantiomers with respect to this carbon. So the first thing that I'm going to flip is going to be the F and the methyl group. So now F is on top, the methyl group is to the right. Secondly, I'm going to flip the methyl group and the hydrogen. And now notice that the arrangement of the atoms are identical with respect to the first chiral carbon. So they are the same. Now let's look at the bottom part. And let's flip the H and the methyl group. And now let's flip the Cl and the methyl group. And so when I flip them twice, then the configurations are identical as well. Since both of them will have the same configuration at both, they are the same molecule. Again, I think this saves a little bit of time as compared to doing RRS. And so best answer for 35 is answer choice C. Let's now consider number 36. We want to draw the lowest energy conformation of trans 1,3-T-butyl methyl cyclohexane. Without wasting any time, we should automatically draw the chair conformation. Again, remember that this is in one plane. I'm going to place my T-butyl group in the equatorial position because it's the biggest and bulkiest substituent. And in the 3 position, the methyl group, since this needs to be trans, the methyl group must be coming straight up. So that means I'm going to have equatorial hydrogens in this position, in this position, and this position, and this position, and this position. That's a total of 1, 2, 3, 4, 5 equatorial hydrogens, and this is also answer choice C. So 36, the best answer is C. Let's now consider number 37. We want the major product, so let's look at the reaction in a bit of detail. Of course, we have our double bond, and we have stereochemistry with the T-butyl group. And we are going to subject this to conditions of borohydration. That means BH3 and THF in the first step, and then hydrogen peroxide and hydroxide in the second step. Remember, this is anti-Markovnikov addition in terms of the regiochemistry. And by anti-Markovnikov, the least substituted carbon is going to be the carbon that's oxidized. So that means the OH is going to go to this position right here. The H is going to go to this position right here. And they will add syn stereochemically. So here's the regiochemistry, it's anti-Markovnikov. Here's the stereochemistry, it's syn addition. Putting all this together, we can draw one of two diastereomers. And of course that double bond's gone now, so I'm going to get rid of that. So I'm going to choose to put the OH coming out, which means the hydrogen would also be coming out, and the methyl group would be going in. So answer choices B and C are incorrect because you have the wrong regiochemistry. Answer choice D is incorrect because you have anti-addition. Therefore, A is the credited response for number 37. Let's take a look at number 38. So we're going to look at an elimination reaction with the following molecule. And as we see, the chlorine is going to be in the equatorial position. We know that we need to look at the ring flip isomer because you must be anti-periplanar. So the deuterium is equatorial and the hydrogen is axial. So I'm going to draw the chair flip. And of course, Cl's coming up. And this hydrogen is equatorial, so that cannot be removed. And of course, this deuterium will be axial, while this hydrogen will be equatorial. So it's the deuterium that's removed. So if I have a base, remove the deuterium, form the double bond, and chloride will leave. This is going to leave me with, of course I'm going to lie a little bit on this, it doesn't have this non-planar conformation as much, but it's nice to draw this. So out out of my carbon-carbon double bond, you can see I will still hold on to the hydrogen. And on this double bond, even though I didn't draw it, there is another hydrogen. And of course, on this carbon, there is a methyl group. So first of all, the deuterium is gone, so we can eliminate choices A and C. Secondly, the double bond is secondary-like. We can eliminate B. So the best answer choice is going to be D. And as we draw this in the planar conformation, lots of different ways to do this. I'm going to show one, not committing to stereochemistry. And of course, both of these guys are hydrogens. That is consistent with response D. So move on now to number 39. I'm going to do two more and then I'm going to close this particular podcast and we'll finish up the rest on the last one. So we have cycloheptane derivative. And we're going to do borohydration. Of course, after the borohydration, we're going to have the anti-Markovnikov alcohol. Then we're going to react this with NaH. That's going to deprotonate my alcohol. So this is going to be nucleophilic attack. That's going to give me an alkoxide. And finally, this is going to react as a nucleophile on propyl bromide. This is called the Williamson ether synthesis. And we haven't been taught this formally in class, but we have learned formally about substitution reactions. So this is something I would expect you to be able to figure out. And you get this compound which is consistent with credited response B. Finally, let's look at number 40 and wrap up this particular podcast. We want the key steps in converting one methyl cyclopentene to 1-cyano 2-methyl cyclopentane. Clearly what needs to happen here is I need to add a good leaving group across this double bond in an anti-Markovnikov fashion. So one of the last mechanisms I taught you this semester, HBr with peroxides. This is anti-Markovnikov. And then we can do nucleophilic attack with cyanide. So we need an anti-Markovnikov addition of HBr and then nucleophilic attack with cyanide. And this is going to be answer choice B. Be a really good idea to review the mechanism for this reaction right here. All right, so I'm going to stop this and we'll do one final screencast to finish up the solutions to the mock final exam.